See how a rotating object bends the airflow, which is why lift is created. While testing this wind turbine, a way to increase Magnus lift was discovered. The traditional method is to add plates at both ends of the cylinder to increase the lift. This video proposes a new way: use blades instead of end plates to further increase lift. When the blade acts to exhaust the airflow from the end, the Magnus lift increases, the drag decreases, and the lift-to-drag ratio increases. When the blade acts to inhale the airflow from the end, the lift force decreases and the lift-drag ratio decreases. Then do an experiment to verify. When the rotor rotates in the wind tunnel, the lift-to-drag ratio is equal to the tangent of the deflection angle, theta. Therefore, the larger the deflection angle, the larger the lift-to-drag ratio. The red rotor uses traditional end plates, the blue rotor uses blades. The smoke blower is 1/4 below the upper end of the rotor. The wind speed is about 2 meters per second, and the rotor rotates at 3,800 RPM. View from the bottom. Overlapping two screens makes it easy to compare the deflection angle of each rotor. The closer the rotor is to the smoke blower, the larger the deflection angle and the larger the lift-to-drag ratio. It shows that the blue rotor is closer to the smoke blower than the red rotor. Indicates that the blue rotor has a larger lift-to-drag ratio, which means higher efficiency. Why so? What is the effect of the blades? Let's see if the smoke paths are different. Split the screen to see if there is something different in the smoke path between the two rotors. The red rotor seems to have a clear boundary from the smoke, and the blue rotor can bring the smoke closer to its surface. Maybe it's because the blades are exhausting the airflow, so the pressure around the blue rotor is lower. This should be the key to reducing drag. Let's look at the smoke path at another height. Move the smoke blower to the center of the rotor, so that the smoke is away from the ends. Observe the smoke path again. View from the bottom. The situation is similar, although the smoke is further away from the blades. The boundary between the red rotor and the smoke is still obvious. The smoke is still closer to the surface of the blue rotor. Indicates that the blade still has an effect on the airflow in the center of the rotor. As the smoke gets closer to the rotor, the more curved the path. Therefore, the centripetal force exerted by the blue rotor on the airflow is larger, and the reaction force causes lift. This may be why the blue rotor could also produce more lift. What are the benefits of using the newly invented rotor? Typical applications of the Magnus effect are wind turbines, aircraft, and ship propulsion. Can wind turbines rotate faster with newly invented rotors? Experiments must be done to verify. Build a simple horizontal axis test bench. The left side uses traditional end plates. The right side uses blades. The motors are set to the same current. Start testing. Record the time it takes for the wind turbine to rotate 30 revolutions. It took 22 seconds and 19 seconds from left to right, respectively, indicating that the rotor with blades increases the speed by 15%, which helps to improve the efficiency of the wind turbine. For ship propulsion, blades are used instead of end plates. Are there any advantages? For traditional rotors, the lift-drag ratio is fixed at the same rotation speed. The direction of the combined force of lift and drag cannot be adjusted. When the direction of the combined force is different from the ship's course, it must be corrected by the rudder, which creates a waste of energy. However, using the newly invented rotor, the magnitude of lift and drag can be adjusted by changing the pitch of the blades, so that the direction of the combined force can be as close to the ship's course as possible, thus reducing the burden on the rudder and saving energy. In addition, can the newly invented rotor make the ship faster? A linear motion test is required. Before the end of this video, a supplemental information is attached. Some people are wondering, can this wind turbine rotate without wind? The experimental results are as follows. Turn off the fan. The wind turbine stops. Turn on the fan again. The wind turbine resumes rotating. Use just one rotor to see if it makes any difference. Change the direction of rotation. Conservation of angular momentum has little effect. The main shaft cannot continue to rotate. Turn on the fan again. The rotor swings violently. Therefore, the turbine is mainly affected by the Magnus effect.